we found Heisenberg from within what I'm calling quantum space, or that area that is ruled by Schrödinger's equation. Now what I want to do is see where do we get to Heisenberg from exterior to quantum space, and why do we have two different spaces? We have two different spaces because the limitation of the nature of light, first off its speed, and secondly because of Maxwell's equations denoting the speed of light as determined by both its frequency and its wavelength, the relationship between frequency and wavelength. So, to explain, I'll put this over here. That's good. Yeah, we're dealing with Heisenberg, and this is from Heisenberg's paper. So where is Heisenberg? What Heisenberg is saying is there's a limit to how well we can measure things. This is measurement, okay? We have a ruler, okay? This is a ruler which has both metric, which is used in Canada and the rest of the world, and inches, which is imperial system used in the United States still. And only the United States. Now, if I have a ruler, and I notice with a ruler I got like ½ inches, quarter inches, and things like that. But if I have a ruler, I want to measure something, let's say something, and the ruler only has inches in it. Let's say it doesn't have ½ inches or quarter inches. So it only has inches. So if I am to measure something and try and measure it, I can only measure it to the nearest inch. So we now have that this can only be measured to the nearest inch. If I have a wavelength of light, and all I have is each wavelength, I don't have half wavelengths or other things like that. I just have the wavelength of light, and I count fringes and other things like that to do in a very, very small measurement. Or I may have wavelengths from electron microscopes, scanning electron microscope or something like that. And the resolution only is as good as the wavelength of what I have. Electrons, of course, have extremely small wavelengths. So if we now have some wavelength, lambda, and we now know that the momentum times wavelength is equal to h, Planck's constant. If this is the case, the wavelength is as close as we can get it. So if I am measuring momentum, the closest I can get, delta p, the error that I will always have in the momentum, times the error delta x, that's the error in the measure, this is really my delta x, would have to be greater than or equal to h. Anywhere outside of that area, I can have a valid measure. Now, so much for space. I now have a watch. And it's an interesting watch. I don't have a stopwatch. It might make it more dramatic, but I have a watch. This is a stopwatch or a countdown timer. And this countdown timer is in seconds. I don't have half a second, quarter second, anything. I just have seconds. So I press the thing, and I can watch it count down. So if I am measuring something that is happening, an event or a duration, I can only measure a duration accurate to the nearest second. If I have light, if I am using light or the frequency of light, then I can only measure accurately to that particular frequency. It's as close as I can get. And this is exactly how Heisenberg explained it in his paper. It's exactly the way Heisenberg did it. So we know E equals h nu from Einstein. Nu equals 1 over the period of the frequency. That's it, right. So we now have E equal to h over time, or ET called home, which is equal to h. That's our error in t. So the error of any measurement of energy will be equal, sorry, E is energy, h is Planck's constant, is frequency. E, then the error we measure in energy, the error we have in time, times the error in energy must be equal to Planck's constant as accurately as we could possibly get it. Therefore, any valid measure, since that's the error, any valid measure in time must times the energy that is required to make the error in the energy to make that particular measure must be greater than h. This is not h bar, which of course goes to against the status quo. It is h. That's the way Heisenberg designed it originally, and these are the original. That's how he got it. If you read his paper, that's exactly what he said. Now, from Heisenberg, we now move to an interesting character known as Lebesgue. I'll try and spell his name, Lebesque, and a man by the name of Minkowski. Minkowski was Albert Einstein's high school teacher, if you can imagine. Minkowski, one of the greatest mathematicians who ever lived. He was working with Ramon and also did work in L1 space from Lebesgue. Now, a Lebesgue measure, L sub p equals, what is this thing? The sum of the norm of x sub I, where that is any measure, to the 1 over p and the entire thing raised to p. That look lovely. Well, what that is a Lebesgue measure. That's the Pythagorean theorem. Pythagorean theorem. We're measuring this. If p is equal to 2, we're in L2 space. So if p is equal to 2, we add up the squares. That's 1 over p. All right. Oh, geez, look at this rate. You take that to the pth power, that's now 1 over p. Okay, so you take the whole thing and find it. So if p is 2, whatever, that would be the square root of the sum of the squares. So basically, we would have a measure of, let's say, r squared would equal x squared plus y squared, giving us Pythagoras' theorem, or if you like, r equals the square root of x squared plus y squared. You square each of the measures and so forth, and then take the square root of it. When we're looking at other things, so for example, we could have ds squared, which is a measure that we're trying to make, sometimes known as a metric, and that would equal minus dt squared plus dx squared plus dy squared plus dz squared. We can now take a measure. This particular metric that forms, now forms a measure within what is known as Minkowski space, four-dimensional Minkowski space, which is what we live in now. This is not, in effect, quantum space. Where a measure breaks down, where we cannot do that, is when we start to hit the boundary described by the Heisenberg limit or the Heisenberg uncertainty postulate. So there is, within existence, a region we cannot measure. This region deals with delta P, delta X, and it deals with delta E, delta T. That forms the boundary conditions here. When we go less than that particular area, we cannot measure it using a measure which is from Einstein, and we cannot measure it using the descriptions by Maxwell's equations, and that is why on the exterior we have to use a real measure, and on the interior we're blind. We can't go in there, we have to use something else, and what we use is a different differential equation, because the differential equations out here collapse, and if we collapse those differential equations, we can then find out what is going on inside. And if we collapse these differential equations out here, we end up with Schrödinger's equation on the inside.